Good afternoon and good morning, everyone. I'm Jingfeng Zhang, a researcher from Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest. The full name of Recon AIP is the Recon Center for the Advanced Intelligence Project. AIP was founded in 2016 as the Research Center for the Next AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We would be grateful if you could visit us in our Nihonbashi office in Tokyo in the near future. Next, let me to briefly introduce our first speaker, Zhuo Wei. Zhuo Wei is a postdoctoral fellow at the Commonwealth Scientific Industrial Research Organization, Australia. Prior to joining the CSIRO, he was with the Australian Artificial Intelligence Institute, the University of Sydney, Technology Sydney. His current research interests include the weakly supervised learning, noisy label learning, and federated learning. Recently, he will be transferring his research to collaborate intelligence applications. Let us hugely welcome Zhuo Wei to give his talk on a framework of weakly supervised learning by semi-supervised learning. Zhuo Wei, please go ahead.
Okay, thank you, Jingfeng, for introducing me. Hi, everyone. My name is Zhuo Wei from CSIRO. I will be starting my postdoc in CSIRO as the Cynthia program. And prior to that, I'm a PhD from University of Technology, Sydney. And I'm pretty honored to present my talk here. And as you can see, my topic is a framework of weakly supervised learning by semi-supervised learning. Here's the outline of my presentation. And my presentation is about a versatile framework of weakly supervised learning, which will cover three small topics. The first one is noisy label learning, and the second one is positive on-label learning, which is also called PU learning. And the third one is the federated noisy label learning, which I also call it FED-NLL. And then I will come to my conclusion. The first part is the general introduction. The recent success of deep neural networks and semi-supervised learning depends on massive but carefully labeled data. However, data samples are expensive and time-consuming to label. So non-expert labeling strategies such as crowdsourcing and crawlers have been widely used to mitigate this problem. However, labeling is not easy due to three reasons. The first one is the insufficient quantity of label data. The second one is insufficient submatter expertise to label the data and insufficient time to label and prepare the data. So this results in different kind of weakly supervised learning setting. Weakly semi-supervised learning is a branch of machine learning where noisy or limited or imprecise sources are used to provide supervision signals for the labeling large amounts of training data in a semi-supervised learning setting. So there are different types of weakly supervised learning, and I'm going to just focus on noisy label learning and positive on-label learning. So what is noisy label learning? Like, noisy labels are considered to be the observed labels which are classified incorrectly. But where does label noise come from? There are different sources of label noise, probably due to the insufficient information such as limited description language or poor data quality. For example, if only a part of disease symptoms are given to the annotators, like he might give the incorrect label diseases. And also mistakes made by these annotators may also cause noisy labels. because annotators or experts are not always correct, and they could make some mistakes. In the CIFAR 10 datasets, this cat and this dog can be easily misclassified by human annotators. And the third reason for noisy label is that the classification is subjective in some cases. For example, the doctors could diagnose the illness of one patient differently. Thus, noisy labels are pretty common in deep learning community. And such unreliable labels are corrupted from the ground truth label. And the second topic I want to cover is positive unlabeled learning. Like learning from positive unlabeled data, aka PU learning, is the setting where a learner only has access to positive samples and unlabeled data. And the amount of unlabeled data is much higher than the amount of positive samples. As you can see, different from traditional supervised learning with both labeled positive and negative labels, there are only labeled positive labels in the PU learning, and while the unlabeled part contains both positive and negative data. However, in this realistic application, in the realistic application, like one certain of the class might not be difficult to obtain or collected or annotated. Here are some examples. For example, while we can label the subscribers who have watched at least one Hunger Game movie as being interested in this game, we cannot be sure like the interest of a subscriber who never watched a Hunger Game before. Similar examples can also be found in disease diagnosis. For example, in chronic disease diagnosis, while we might consider a diagnosed patient to be positive, the much larger population of undiagnosed individuals are particularly mixed with both positive and negative samples. Since people might be undergoing the disease incubation period, or they might just have not seen the doctors. So if we roughly label the undiagnosed examples as the negative, like this will lead to biased classifiers. So it will inevitably underestimate the risk of the chronic disease. Moreover, like from a different scenario, like weakly supervised learning might not be always centralized. As you can see, the figure demonstrates learning with noisy labels in different institutions like hospitals, medical research center, or community hospitals. Like the labels of the local data are not annotated by the same clients according to the same criteria. So they may contain different noises across clients. So it has been widely demonstrated that in the centralized setting, the wrongly annotated labels can cause severe failure of the machine learning models and quickly result in overfitting to wrong labels. So in this decentralized setting, or we can call a data island, this problem can be more problematic because the server cannot directly access the data and filter out the noise. Thus, it's very important to figure out how to teach neural networks to learn from noise labels under the setting of federated learning. And next, I will dive deep into the three topics I want to talk about. The first one is noisy label learning, which is a brief introduction of how to combat noisy labels in centralized settings using semi-supervised learning. So as I just introduced before, there are different kind of noisy labels. And I guess there's a problem. Should I answer it now? Or hi, Jinfeng. I think there's a question in the chat box, but I'm not sure whether I can see it.
No. It is me who call for questions. If there are any, I will let you know.
Oh, okay. Yes. there are different kind of noisy labels, and first kind is the synthetic noise, which is to mimic the determined process of human brain when labeling. For example, in the CIFAR-10 dataset, we as a human being might misclassify this dog as cat. So we just need to flip the label of the cat to the dog manually to mimic this process. Also, a common and less expensive way to collect large dataset is through online search engines. For example, we use the search engines to enter the the keywords, and then it can generate a series of corresponding pictures. In addition, there will be some explanatory text near the picture. By extracting the keywords in the text, like one can get the category information presented in the image. Using the above methods, a large number of labeled images can be obtained quickly. However, using search engines for labeling might bring noisy labels to the collected dataset because the surrounding text might be wrong. So these noisy labels cannot provide strong supervision information for deep neural networks, which will lead to severe performance degradation. For example, in this data set, which is called Closing 1M, it leverages you use some crawlers to download images from Taobao, I guess, and probably there are 1 million images of closing, and the approximate noise ratio is 40%. Then here comes the question: how does noise label affect deep neural networks? So when deep neural networks are trained on the dataset with noisy labels, their predictions may oscillate, which will show a certain kind of instability. As we can imagine, like from the perspective of the deep neural networks, the clean label will tell you that this photo is a cat, and then the wrong label or the noisy labels will tell you this photo is a dog. So, but both of them will calculate the loss function values and affect the parameters of deep neural of the model through backpropagation. So this is so problematic. And also there's another important aspect that deep neural networks will first learn the correct labels, and then it will learn the noisy labels. So from my personal experience, when I conduct experiments, like I will find it is easy for me to observe that the accuracy continued to rise at first, but it seems that seems like there are no label noise at all. I mean, at early stage of training. But as the training proceeds, it starts to fit the noisy labels, and as a result, the accuracy will begin to drop sharply. So in the right image, as we can see, even in a data set as simple as MNIST, when the noise ratio is pretty high, the robustness and generalization ability of our model will degrade on a large scale. So how do previous study tackle noisy labels, and what challenges are they facing? So I'm going to briefly introduce 3 previous studies. The first one is called noisy estimation matrix method. For this type of methods, it uses some heuristic methods or even some clean data to calculate the noise correction matrix TX. For example, if the data set has only 10 classes, then the matrix is 10 multiple by 10 matrix. And then by multiplying this matrix by the prediction of the model, we can get a more accurate prediction result, which is to say that we can to some extent correct the prediction of the model. But a problem faced by this method is that it is difficult to estimate this TX because after all, it is still difficult to convert the wrong into the right, especially when there are many categories in the dataset. And another type of the method is the sample reweight method. As I mentioned earlier, deep neural networks learn easy patterns first and then overfit to noisy labels. Thus, researchers in this line use meta-learning or curriculum learning to reweight or readjust different loss values to different samples by giving different weights to mitigate the influence of the noisy labels. For example, in the picture below, there are images that shows all the samples which are supposed to belong to the category of jacket. But there are some windbreakers and pants that are wrongly marked as jackets. So the weight multiplied by their loss value will be relatively small, like 0.3 or 0.2. But if a picture of a it is a picture of a jacket, then its loss value will be multiplied by a relatively large weight, for example, 0.8. However, these methods also have some disadvantages. Like no matter how much you reduce the weight of the noisy data, it still exists and it will still affect the performance of the deep neural network. The third method is called sample selection, which is a method that aims to completely remove the influence of the noisy data. And these lines of methods leverage the small loss trick by only selecting a portion of samples with smaller losses to train the model. Because as I just mentioned, like these samples are often considered to be clean samples. So training with these small loss samples can greatly reduce the impact of noisy data. However, this type of methods directly discard some samples with large losses. And the problem is that these samples may also contain some important or useful information from because the associated image associated information in the image might be huge enough for us to learn something. And also, and when the noisy ratio is relatively high, throwing away the large loss samples may lead to insufficient training data. So one of my early research problem becomes how do we leverage the image content of the unchosen or we can say noisy labels. So is there a way that we can both select clean samples and leverage the unselected big loss samples instead of just discarding them without further thinking? There's a classic paper that bridges the gap between noisy label learning and semi-supervised learning, which kind of perfectly solves these problems. And it is called divided mix. Like on the picture on the right is a simplified process of this paper. It first uses Gaussian mixture model, which I prefer to call it GNM, to divide the entire data into clean data XE and noisy data UE. And then it retains the label of the clean data, but discards the label of noisy data, and which turns the scenario into a semi-supervised learning setting. And meanwhile, it also leverages the training mechanism using two networks for co-guessing and co-refinement. And these two co-guessing and co-refinement techniques greatly improve the performance, the accuracy of the methods compared to previous methods. And first, I will briefly introduce Gaussian mixture models to distinguish clean samples from noisy samples, because my method also uses also kind of involves this method. First of all, GNM is an unsupervised clustering method, and on the right side, this is a normal distribution of loss values for clean samples and the noisy samples. So divided mix will put the loss value of each sample into the Gaussian mixture model to find out which cluster it is. Like in other words, probability WI is given to each samples to indicate the probability of it being clean. So in this method, we will set a threshold for detecting clean, for distinguishing clean and noisy samples. When the probability of the sample being clean data is higher than this threshold, we will put it into the label set for semi-supervised learning. And when the loss of a sample is lower than this threshold, we will remove the annotated label and only keep the image content. So this labels without these images without labels will be put into unlabeled set. And divided mix use mix match as the semi-supervised learning backbone. Mix match like randomly breaks up the label set X and unlabeled set U, and then just linearly combine the images and labels to get new X pi and U pi, and then it used the divided mix used the cross entropy loss for the unlabeled samples and the mean square loss for the unlabeled samples to update the deep neural network. So I think my framework was like a part of my framework is inspired by divided mix. Like to think deeper why GNM is used as the sole sample selection method to divide noisy samples and clean samples. Because I have tried some other clustering methods to distinguish clean and sample methods. For example, the word linkage or the fuzzy C-means, because I think as you can see in this distributions, I think there are some hierarchical things between these two distributions, and also some parts of the noisy samples and the clean samples are kind of overlapped. So I thought these two clustering methods might be better than GNM, but after I run the experiments, the results were not satisfying enough. And probably I should conduct more theoretical investigation on that. But my point is, like there are many methods that can be used to distinguish clean samples and noisy samples. And also there are other studies which focus on dividing clean samples and sample selections like self, like, yes, I think there are probably a few researchers focusing on that. And also there have been voices from different papers which support BNM, which is a beta mixture model, which supports BNN instead of using GNN. So, there's no standard answer for which sample selection methods that we should use to distinguish noisy samples and clean samples. And I think the situation is quite the same for semi-supervised learning backbones. So why do we have to use mixed match? And also, like, semi-supervised learning community is growing very fast, and there are many methods there are many state-of-the-art methods which beat the performance of mixed match, and I think there'll be many more to come, like in the future. So my perspective of thinking becomes whether we can find out or discover a meta or once-for or versatile framework that can utilize the power of any sample selection, any sample dividing mechanism, or semi-supervised learning backbones. So in a nutshell, in previous literature review, a few works have studied sample selection in noisy label learning community, and also SSL community is also developing very quickly, and I think SSL methods can be used to leverage the unchosen noisy samples in the whole data set. So and also these two methods can be naturally combined to combat noisy labels. So my final research question becomes: can we develop a versatile framework, like a holistic framework, or a universal framework that combines that can combine different sample selection and semi-supervised learning backbones to combat noisy label learning? Thus, we propose a framework to combat noisy labels. So it consists of two components, which are marked in red, which mark in black. Yeah, the dividing strategy, or the sample selection strategy, and the semi-supervised learning. So using the sample selection strategies, we can divide the whole data set into a clean set and a noisy set. For the clean samples, we'll keep both of the images and the associated labels. But for the noisy samples, we will discard their corresponding labels. Also, one thing that I want to mention is that our framework uses mini batch sample strategy instead of epoch batch sample selection. So my mini batch sample selection strategy divides the whole mini batch of samples into the clean subset XM and the noisy subset UM right before updating the network using semi-supervised learning backbones. So there are some disadvantages of my mini batch sample selection versus epoch sample selection. For example, it can avoid the confirmation bias of dividing data sets, and also it can improve the computational efficiency, and it can inject some randomness to the whole dividing and semi-supervised learning process in order to avoid selecting the same clean samples all the time. And also it can just keep the model for sample selection up to date. Here's the pseudocode of our algorithm, which is called semi-NLL. It is a framework that can utilize the power of any sample selection strategies and semi-supervised learning backbones. To do that, we only need to replace the placeholder select and the placeholder semi to with specific sample selection strategies and semi-supervised learning backbones. Also, one of my contribution is that we propose new sample selection strategy, which is called self-prediction divider (XPD), to divide the clean and noisy samples. Because deep neural networks predictions tend to be consistent on clean samples and inconsistent on noisy samples. So based on this phenomenon, SPD selects the correct samples by the agreement between the original labels and models on prediction. As you can see, what I had here is the max number of the softmax predicted by the original network. And as for the clean set, if the pseudo label is equal to the original annotated samples, then we will regard these samples as clean samples. Otherwise, we will put them in. We will regard them as the noisy samples and put them in the unlabeled set. As for the semi-supervised learning methods, aside from mix match, I also use two semi-supervised learning backbones. The first one is temporal ensembling, which is very classic semi-supervised learning methods, which use the EMA of the label prediction from parse epoch as a target for the unsupervised loss. And also the method pseudo labeling is not the method of the semi-supervised learning it's not the actual name of the semi-supervised learning. I just use pseudo labeling for convenience, and it is published in 2020 at IJCNN, and this method learns from unlabeled data by combining like soft pseudo labels generation and the mix-up argumentation. As you can see, these are the instantiations of our framework, and like for example, GNN is the clustering method I introduced, and SPD is the method I propose, and also there are some semi-supervised learning methods. So since our framework is a plug-and-play algorithm, you can instantiate it using any semi-supervised learning methods and the dividing strategies. But we found the instantiation of our framework, GPL and divided mix plus, achieved the best accuracy across 4 data set, which are MNIST, Fashion MNIST, and CIFAR 10 and CIFAR 100. And also, it is happy to know that dividing mix plus, which is an instantiation of our framework, greatly improved the performance, like greatly surpass its competitor divided mix. And these are the experiments on real-world data set. CIFAR, I think there are 4 real-world data sets, and I will briefly introduce like all of them. Closing 1M is the data set that consists of 1 million training images from online shopping websites with labels annotated from surrounding texts. And the estimated noisy label, the estimated noisy ratio is about 40%. And web vision is real-world web noise dataset, and this is a mini version of web vision, which use Google subset image of the top 15 classes. Otherwise, it will be too large. And Food 1 and Food 101N is a dataset contains food classification, and I think there are more than 100 classes collected from the web. The estimation of the label purity is 80%, so the noise ratio is approximately 20%. And also the animal 10N contains 10 animals with confusion appearance downloaded online. And two of our best instantiations, GPL and dividing mix plus, achieve the state-of-the-art performance on these 4 real-world data sets. We also conduct experiments on CIFAR-10 to demonstrate the sample selection, to demonstrate the precision and recall of our sample selection methods. And as you can see, our instantiations of the top 2 lines greatly outperform other baselines in both dividing in both precision and final accuracy. And it also shows the benefits of using semi-supervised learning methods in our framework, which can improve the semi-supervised learning performance incrementally. And we also visualize our methods by TSNOE plots, and we can see the representation learned by our instantiations, GPL and divided mix are more fragmented and pushed away from each other, which showing the better isolating capacity of our instantiations. Also, like our framework, the instantiations from our framework have advantages when it comes to training time. Divided mix plus is much faster than its competitor divided mix, and showing that our framework work more efficiently than simply combining semi-supervised learning and sample selection strategies. And are there any rules for this framework, or can we just combine, can we just figure out or discover more synergy combinations? So we conduct a holistic comparison on the CIFAR-10 dataset. We basically combine all the semi-supervised learning methods and the sample selection methods we know, like these are the results on CIFAR-10, and we have some conclusions for semi-supervised learning and sample selection strategy. For example, the rules for choosing sample selection strategy is that it depends on whether it is symmetric noise or asymmetric noise. If it is if you want to use it in a data set with symmetric noise, I think GNN is better than SPD, and vice versa. And as the rules for sample selection, as the rules for semi-supervised learning backbones, I think we should choose the correct, not the correct, the suitable semi-supervised learning methods for different noise ratio. For example, when the data set are kind of imbalanced, probably we can choose some semi-supervised learning methods that can better deal with imbalanced data. Also, we are happy to find out the most synergy pair, which is GNN plus pseudo labeling, and it achieves the best performance on both symmetric and asymmetric noise. And we believe its superior performance benefits from the conceptual simply idea of pseudo labeling to reduce the confirmation bias generated from the sample selection process. And also, please be noted that the pseudo-label learning, the pseudo-labeling methods is not published on top conferences. That being said, we will keep exploring the possibilities of more combinations of sample selection and semi-supervised learning based on our framework to figure out the chemistry in between, instead of just simply piling up state-of-the-art methods published in top conferences. And the second topic is PU learning, which is to use semi-supervised learning to solve PU learning methods. And our framework can also be used to solve the problems in PU learning. So here's the background of PU learning. Like I've conducted some literature review and found out that current importance reweighting methods treats unlabeled data as negative data with importance weights. And I've done some pilot experiments, and I found out that the importance reweighting methods might suffer from severe overfitting problems because the unlabeled data in the few learning methods can be treated as negative noisy labels. So my research question for PU learning becomes, can we transfer PU learning to noisy label learning settings? So after we transfer the PU learning to noisy label setting, then can we apply my framework to solve the PU learning using semi-supervised learning? Here's the experiment. Here's the pilot experiment I have done on CIFAR 10, and we can see this is the positive probability of the unlabeled data. I think there are histogram of the these are the histogram of the previous state-of-the-art methods at early, middle, and late stage of training. And you can see clearly that at the late stage of the training, we observe that more negative samples are misclassified as positive ones, while almost no positive samples are misclassified as the negative ones. I think that has something to do with the previous state-of-the-art method, which treats reweight the unlabeled samples by just regarding them as the wrongly classified negative samples. So I just simply transfer my framework to another setting, to PU learning setting, and propose a simple yet effective end-to-end semi-supervised learning approach to tackle the overfitting problems caused by previous importance reweighting methods in PU learning. To review the above issue, we just combine the dynamic increasing strategy and the semi-supervised learning backbones to effectively distinguish the samples in the original unlabeled set. And this square represents the original unlabeled set, and dynamic increasing sampling is a method that's similar to sample selection. We just select the most confident positive samples and negative samples, and then we just regard them as the clean samples or as the correct samples with positive labels and negative samples. And of course, the rest unconfident samples are regarded as the unlabeled set in order to leverage in order to better leverage their image content. So here's some simple experiments of our methods compared with SOTA PU learning methods, and our methods have achieved the best accuracy across 4 data sets. And the third topic is federated noisy label learning, which is to combat noisy label learnings in federated learning setting instead of centralized setting. Here's the a brief background. I've conducted some. I see some papers in this field, and there are some related methods which are robust federative learning and personalized federative learning methods, and also there are some methods which directly apply sample selection methods in like from the noisy label learning community to the federative learning community. But I think previous federative learning methods are not robust enough to noisy labels, and previous noisy label learning methods just focus on centralized data. So we cannot just apply this message to federated learning settings directly. And there's another problem that we tend to ignore, which is noisy label learning in federative learning settings is actually much more time and computational consuming. So my research problem for combat noisy label learning in federative setting becomes how to combat noisy label learning using the sample selection in semi-supervised learning setting, and how to reduce the communication and computation cost in this setting. Here's a preliminary studies about which gives you a brief introduction of the classic federative learning. Like, for example, we consider image classification in FL. So there's a global model which is updated by aggregating K local models on Clay clients. So in federated learning, the global model theta aims at minimizing the total loss over all clients. And most federative learning address the above of optimization problems by iterating between the local updates per clients and the global aggregation of the uploaded local models. Specifically, the local updates on device K starts from initializing initializing theta to theta K by downloading from the server, and then minimize the local loss LK by multiply by multiple epochs of gradient descent. However, in the present, if there are noise involved in different local data sets, the local update can quickly overfit to the label noise in the local data sets, and which will result in poor local models. Moreover, directly aggregating these models will lead to a global model with poor generalization performance. So therefore, an intuitive motivation is to elevate the above problems, which is to select high quality local models only for aggregation and select clean labels on each device to update the local model. So we propose a two-level sampling methods. Our methods first conducts client sampling to select high-quality local models for robust global aggregation, and then it is followed by local data sampling that selects clean samples and correct pseudo labels of the local updates on each client. As for the client sampling, we will estimate the noisy ratio of a client K by evaluating the correctness of the samples label using the confidence score computed on the latest global model. And for the local data sampling, we will sample training data for each local client according to their confidence score computed on the global model. And as you can see, when we do evaluation to calculate the score of no matter the clients or the samples on the clients, we use the global model because it is proven that global model is more robust than the local models. Also, a bottleneck for directing applying noisy label learning to local updates on each device in federated learning is the inefficient local training data. And this problem will easily lead to overfitting of local models to noises. So for samples with incorrect given labels, their input features contain even richer information than their labels. But if we cannot leverage this huge amount of labels, then we can only select samples with clean labels for training. So I think this is the place where we can use my algorithm to improve the performance by better leverage the unlabeled samples in this scenario. And And then we apply a recent semi-supervised learning method called fixed match to better leverage this unlabeled samples. In particular, fixed match selects the high confidence samples. Fixed match selects low confidence samples in this unchosen set, and then relabel them by model predictions. For example, their pseudo labels, as you can see Y here, which is defined as the pseudo label of an unchosen sample. Yeah, and the pseudo label is the max digits of the softmax output, and also the pseudo labels are estimated over multiple weak augmentations to ensure that the labels are correct. And then it minimizes the loss on this unlabeled data using strong augmentations. And the second problem is the computation and communication costs. Since noisy label learning usually converges much slower and is less stable when learning with clean compared to learning with clean labels. Another key challenge is how to improve both the computational and communication efficiencies. So thus we propose some possible schedules of local epochs, and discovered that if we start from like more local data sets and progressively reducing the number according to certain decay functions, we can achieve better trade-off between the computation and computational efficiencies than just fixing the number of the local epochs. So thereby, as the quality of the selected samples and samples improves quickly, we can just reduce the local epochs to encourage more frequent knowledge sharing between different clients and boost the global model performance. Yes, so we compare our methods with baselines that directly combine existing methods from FL community and noisy label learning community. Like each of our baselines applies and noisy labeling methods to local update within an within a federative learning algorithm. So for federative learning, we choose 4 algorithms covering the representative federative learning methods. For example, Fed average and APFL, which is personalized federative learning. And also we choose 2 robust federative learning, which are CROM and CFL. For noisy label learning, we consider 2 sort methods, which are divided mix and JOSRC. We denote this baseline in the form of FL plus NLL. So in the experiments with homogeneous and heterogeneous dataset distribution and different noisy ratios, it is exciting that we observe that the direct combination of SOTA federative learning methods with SOTA noisy label learning methods can easily fail in some hard scenarios, but our methods consistently achieve better and robust performance. Also, to verify the effectiveness of our two level sampling, we compare 3 different methods. One is the original methods, which use the proposed two level sampling, and the second one is the uniform client sampling. Uniform client sampling, which choose the clients uniformly while conducts local data sampling, as described in our 2-level sampling. And of course, the third method is the methods with uniform local data sampling, which means that we just keep the client sampling as our 2-level sampling, and as for the local data sampling, we just use uniform. We just use we just choose the samples with uniform probabilities, and of course our two-level sampling methods achieve the best performance compared to these methods, demonstrating that the benefits of our two sampling methods. And here's the contribution of this paper of the third topic. Is that we propose two-step sampling methods for federated learning with noisy label, and we also studied two schedules of local epochs to achieve better trade-off between the communication and computation efficiencies. And also we have conducted extensive experiments to demonstrate like our federated learning methods will constantly outperform the trivial combination of federated learning and noisy label learning methods. So that's the end of my presentation. Thank you for your time, and feel free to ask questions. To ask me any questions.
Yeah, hi audience. If you have any questions to Joey, please feel free to ask. Actually, I have a question in terms of your framework to model the noisy label learning. By my memory, I think divide mix already use the idea that use the semi-supervised learning to model the noisy label learning. So based on this fact, what's your contribution on this part?
Yes, it is a question that are often asked by my reviewers, and I think one of the biggest contribution of my work is not the performance or the novelty that's brought by some specific methods. One of the biggest contribution of my paper is this versatile framework that utilize like different semi-supervised learning and sample selection methods, and you can use not only GNM or BNM. You can use all the sample selection methods you want, and you can integrate it different sample selection method and semi-supervised learning methods to our framework without any extra cost. And also, like, since we propose mini batch sample selection schedule, so this schedule can better improve the performance compared to previous dividing strategy, previous epoch levels strategy. So I think the versatility, the convenience of this framework are my biggest contribution. And also I extend this framework to PU learning and federated learning. So this framework, I think this is just a plug and play algorithm that you can apply to different scenarios to solve different problems.
I see. Thank you very much. Got it. Okay, again, thanks, Joey's great talk today. Yeah. If there are no further questions, let us welcome our next speaker. Nicola is a postdoc fellow at the ETH AI Center, working under supervision of Martin and Fanny. His research interests lie in the area of trustworthy machine learning with focus on robustness and fairness. Before ETH, he was a PhD student at RST Austria, working in the group of Professor Christoph. He was also part of ELLRS PhD program. Let's welcome Nicola to give his talk on statistic aspect of trustworthy machine learning. Yeah, please.
Thank you very much for the kind introduction, and let me also begin by thanking you for inviting me here. So this talk would be about certain statistical aspects of trustworthy machine learning. So essentially, how much data would we need for learning certain robust or fair models. So I guess that this slide is now obsolete, but as was already mentioned, I'm a postdoc at ETH, and I work with Martin Vetchev and with Fanny Young. And before that, I was at IST Austria and at Oxford. In terms of research interests, I'm mostly interested in trustworthy machine learning. And one's particular aspect that I have been focusing on is learning from unreliable training data. And in terms of the techniques that I use, I'm mostly interested in theory, so in things like statistical machine learning, but also in optimization. And I also try to experimentally validate the algorithms that I study as well. So if you can click on the next slide, please. Thank you. So yeah, so I think that given this venue that I'm speaking at, there is little need that I justify why it's important that we make machine learning more trustworthy. So in applications like in healthcare and in automated job application processing, it's super important that we ensure that our models come with reliability guarantees, or otherwise people just wouldn't trust them enough to use them instead of human decision makers. And among these guarantees that we need are robustness to training data issues, and of course also fairness, so ensuring that our models are sufficiently fair. And there is many other aspects like explainability, privacy, robustness at test time, and many others. If you can click, please. Yeah, so hold on, please, on the previous one with the blue.
Oh, okay. Yeah.
Yes, yeah. So so in this talk and also in most of my work, I have focused on these first two aspects. So robustness to issues with the training data and also fairness. And also notice that, of course, those two are quite related because very often the underlying reasons for the unfairness of our models is issues with our training data, like underrepresentation of certain groups and also some aspects of bias and data corruption that enter. If you can click, please. So in this talk, I'll tell you about the two projects that I have been working on for the past few years. So the first one will be about fairness-aware learning from corrupted data. So essentially, this is on the intersection between these topics that I mentioned, and I would ask how much we can learn when our data has some corruption inside it, and can we achieve fairness in such contexts. And in the second part of this talk, I would focus on robust learning from multiple data sources. So this would mostly focus on robustness, basically learning from corrupted data. But at the end, I would also very briefly touch on the fairness aspect there as well. If we can go to the next slide. So here, moving to the first project, I think that you all know that machine learning models are nowadays widely adopted, and they achieve state-of-the-art performance on many different tasks. But at the same time, they also often make it into the news for all of the wrong reasons. So in particular, very often we hear that our machine learning or AI models are unfair. And I give here two examples. One of them is about an NLP model that is used by Facebook to automatically detect inappropriate content and also fake news. So it was found that this model works very well for common languages when there is lots of data. So, for example, for English, and at the same time, it is really not doing a particularly good job on languages where there is less data. So basically from smaller countries, etc. And on the right, there is an example of a healthcare algorithm that was also found to be unfair. So basically, in this case, this algorithm would very rarely prescribe treatment and further checks for Black patients. And on the other hand, it would often do that with white patients. So in both of the cases, when you actually look inside these articles, you will find that people looked into what is the actual reason for this unfairness. And in both of the cases, it was found that this was actually issues with the training data that propagated and were amplified by the machine learning models. So in the first case, it was mostly underrepresentation, and in the second case, it was the fact that yes, there was probably less data for Black patients, but also maybe there was some historical bias in the decisions that were actually taken in the past by healthcare practitioners. So, given this type of motivation, we were asking in this project how much we can hope for when we're learning models, and we also try to make them fair in the context of having corrupted data. So essentially, how much we can learn statistically from data that is corrupted, and can we make our models fair in such a situation? If we can move to the next slide. Thank you. So I will now introduce our formal setup, and I will begin with the clean data case first, and then I would explain how we would model corrupted training data. So we will work in the context of group fairness and in binary classification. So we are learning a hypothesis that is taking some inputs and it is assigning them some binary labels, and we would also be given access to some information about a protected attribute. So for simplicity, let's just assume that it's binary here. And so our training data would be not only input-output pairs, but also there would be information on this protected attribute. So each of our data points would be a triplet that is input, protected attribute, and output. And since we're currently doing clean data, then we would begin by assuming that this data set is high ID from some target data distribution. We would be learning a hypothesis from some hypothesis space, and our goal is to ensure that this hypothesis is accurate, which means that its risk would be low, and also doesn't discriminate with respect to the protected attribute. If you can click, please, thank you. So then, of course, there is this question: what is the fairness notion that we would use? Like, what does it mean that the classifier doesn't discriminate with respect to the protected attribute? So in our paper, we have considered two fairness notions that are quite popular. In this talk, I would focus on demographic parity, which simply states that the decisions of our classifier have to be statistically independent from this protected attribute. And this independence holds with respect to the target data distribution D. In our paper, we have also looked at equality of opportunity. And so basically, this is our constraint, our fairness notion, but in practice, of course, it is difficult to ensure that a classifier would be exactly fair. So instead of that, we can also measure the amount of unfairness that the classifier has. So we can do that in this binary case by looking at difference between the conditionals, basically, like basically how does the probability of a positive classification change when we change the protected attribute. And we would look at the absolute value as a notion of fairness deviation. Yes, thanks. If we can move. So in this talk, how challenge this assumption of PID data. So basically, we would move beyond that and ask what happens in case that our data is corrupted. And like notice that in this clean data case, a classic approach of learning would be just that we estimate some empirical risk, like we would look at the empirical risk and some notion of empirical unfairness, basically approximating gamma by some empirical terms and jointly minimizing those maybe with some extra tricks and regularization, etc. But in general, like this problem with the clean data has been very well studied, and we're now trying to move beyond this IID assumption. If we can go next, thank you. So in practice, of course, like real world data can be corrupted, and this can be due to various reasons, including just noise, like doesn't need to be malicious. Maybe this is just some random errors from recording our data and like noise, etc. It can also be due to some systematic biases, and especially in the context of fairness, we unfortunately do expect that in our data maybe there is some historical bias. And then lastly, you can even expect, especially if you gather data from the internet, let's say, then it could be that there is even worse case data manipulations. And at the same time, there is all kind of problems that can occur with our data, but at the same time, what we hope for is that we certify that our models are fair or approximately fair. Like this is really a property that we ideally want to have to be guaranteed, because this matters and it's important, and it is often a constraint that we should consider. And so in this context, we thought about trying to certify our models even in the presence of worst case data manipulations. So if you can be robust to worst case manipulations, then you can also be robust to all problems that I mentioned before, and also to other problems that we couldn't foresee. And so previous work, when we were starting this project at the end of 2020, actually, there was not much work on the fundamental limits of learning with fairness when you have corrupted data. So there was lots of work on the clean data case. There was also work on learning where you have different specific problems with your data, let's say label noise or protected attributes noise, or a combination, but like nothing on this worst case type of manipulations. And on the worst case side, there was some empirical evidence that poisoning attacks can impact our learning. But what we ask here is, what are the fundamental limits of how much we can learn theoretically from such data? If we can go to the next slide, thank you. So now, I would explain now what is basically the way that we modeled worst case data corruptions. So what is the process that is generating our data? And so we will use here one classic model that is called the malicious noise model. It was introduced by Leslie Valiant, and it works as follows. So first, if you can click, please, there is a clean data set. So like this is this has data set that is on the left. So this data set consists of blue points, meaning that they are not yet corrupted. So each blue point is a triplet that is one of our data points. This is input, protected attribute, and a label. So at the start, these data points are sampled from some target distribution D, and this is a clean data set. So then, click please, there is each of these blue points gets independently marked with some probability alpha. So basically, there is a subset of these points that becomes red, and like these are these points that would be accessible to the adversary. Those are the mark points. So then an adversary comes in and it can observe the training data. So it can observe the blue points and the red points, and it has the power to arbitrarily manipulate the red points. So what happens is that these red points become these devil faces. So this just means that these points were replaced in an arbitrary manner. So the only restriction that we put on our adversary is that it can only touch the red points, not the blue points. And so in particular, this means that the adversary can act with the full knowledge of the problem, and this includes the training data and also the learning algorithm and even the data distribution. So this is an extremely worst case adversary. And then what we're interested in is what are the limits of how much we can learn from this corrupted data set SC. So the learner is just a function that would take this corrupted data set SC. It would output some hypothesis, and the question is, what can we say about the risk and the unfairness of this learned classifier? Thanks, yes, we can move. So the first result that I'll show you is a hardness result that gives basically what are the limits of how much we can hope for with any learning algorithm. And here there will be two parameters that are important. The first one is the corruption ratio alpha. So clearly when more points are corrupted, we expect that our job as a learner is harder. And the second parameter is this minority group frequency, which is just the frequency of the rarer of the protected groups. So if this tau is small, this means that essentially we have very imbalanced data. Basically, our clean data distribution comes with the fact that one of the protected populations is underrepresented naturally. So intuitively, this would also make the job of the learner harder, because this would mean that there is less data that is coming from one of the protected groups. And so then this theorem formalizes these intuitions. So what does it say? Like basically, if you fix any values for these parameters, then there would exist a hypothesis space that is very simple, actually, like a finite hypothesis space that cannot be learned by any learner. And then what do I mean by that? Well, this means that there will be no learners, so no function whatsoever that will do well. So if you take any learner that you like, so a function that is taking data and outputs a hypothesis, then there would always exist a certain difficult distribution and an adversary that with constant probability would manage to ensure that this learner doesn't learn a good hypothesis. And like, what do I exactly mean by that? So if you look at the equations, then recall that SC is our corrupted data. This is what the learner works with. So the learner takes this data and outputs a hypothesis. So L of SC is the hypothesis that is learned by the learner. And we've shown that the risk of this hypothesis and the unfairness of this hypothesis are both far from the risk and the unfairness of another hypothesis. So this means that this H star, which is some other hypothesis, is doing much better both in terms of the risk and in terms of the unfairness. So in particular, the learner has not managed to reach any optimum, neither for the risk nor for the unfairness. And so notice that this result is independent of the sample size. So this holds even when our data grows to infinity. And then it's also informative that we would look at the terms, basically, like what are the irreducible terms that we cannot avoid. So for the risk, this is basically just alpha. And this was actually known. So within the malicious adversary model, it was known that the adversary can always ensure that the learner doesn't reach a good hypothesis in terms of accuracy, and it's suboptimal up to order alpha. This was known. But what is novel here is first that in addition, the unfairness can be made high simultaneously. And it's also interesting that we also look at the specific term there. If you can click please here. So basically what happens is that there is a term that is proportional there to alpha, but at the same time, it's inversely proportional to tau. So recall that tau is the frequency of the error of the protected groups. So basically this means that as soon as one of our groups is underrepresented in our data, then tau is small. And this means that even very tiny amounts of corruption, so even a relatively small value of alpha, can still mean that the learner cannot recover a fair hypothesis. So this formalizes this intuition that, like, when we have more underrepresentation, then even very tiny amounts of issues with our data can lead to some pretty catastrophic fairness. If you can click, please. So, okay, these were lower bounds, and like it's interesting that we look at, can we actually achieve these lower bounds? Like, okay, this is pessimistic, but if our alpha would be small, then it's still important that at least we can do as well as possible. And for these reasons, we have also looked at lower bounds and at upper bounds, sorry. And for this, we have constructed intuitive learner, so kind of one method that you can learn that will achieve performance that is comparable up to constants with these lower bounds. And so what did we do? Basically, we have studied this algorithm, LPRM of alpha. So what it does is that it takes this corrupted data set that it has access to, and it just minimizes a certain notion of lambda-weighted loss. So what it does is that it looks at the empirical risk of hypothesis, and it also looks at some empirical version of this fairness deviation that are introduced. And so basically then it is weighting these terms and it's just minimizing this weighted sum across the hypothesis space. So then we have proven that essentially this learner achieves good performance for any distribution and any adversary. So the formal claim is that for any distribution and any adversary, as long as the VC dimension of H is finite, and we have a big enough data set, then with high probability, the output of our learner would be good. And what does that mean? So it means that if you look at the left, then this is just the lambda weighted loss now on the population level. This is test time loss, and it's lambda weighted between the risk and the unfairness. So this loss of our learner is close to the optimal lambda weighted loss plus 2 extra terms. So if you can click now, then you'll see the first term. Can you click, please? Yeah, thank you. So the first term, well, these two first terms, basically, they are up to constants the same as our lower bounds. Basically, they are of order alpha and of order alpha over tau. So this matches lower bounds up to constants. And if you can click again, then there is the second term. This depends on our data set and on the VC dimension. So basically, this is the classic finite sample terms that you can expect when you deal with such problems, and then this term would disappear with infinite data. So recall that our lower bounds hold for any size of the data, and so then if we look at the infinite data limit here, then this term disappears, and we recover the lower bounds up to constants. And the last thing that is important that I note is that this upper bounds holds for any hypothesis space with a finite VC. So essentially, this learner is a universal learner for all these hypothesis spaces, and our lower bound holds for a specific hypothesis space that is simple, basically finite one. So in particular, also of finite VC. And so this means that essentially, like, these upper lower bounds are matching in the sense that there is no learner that can do better on all these hypothesis spaces of finite VC. If we can move on. Thank you. So you can find more results in our JMOR paper, including on equal opportunity and also some component-wise upper bounds when you prove things independently for the risk and the unfairness, not only for this lambda weighted term. And lastly, we also have some results on the actual rates that you can achieve in terms of the sample size, and in particular for realizable pack learning, we showed that you can achieve some faster rates of convergence. Thank you. Yes, we can move. Okay, so then the second part of this talk will be more optimistic because I showed you hardness result that we cannot overcome in the first setup, and as I mentioned, this was already known in the case of accuracy. So it is natural that we ask, okay, like, these are very worst case manipulations, but are there some situations where we can make a few more assumptions on our setup and be able to protect ourselves against these worst case adversaries and then learn good hypotheses when we have more and more data. So in the second part of this talk, I will talk about one situation where you can do that. So we will mostly do it in the context of supervised learning without fairness. Basically, now we will be just interested in the accuracy of our models, but then at the end, I'll also tell you about fairness result as well. So if we can move, thanks. So the setup that we'll look at is basically learning when our data comes from multiple data sources, and this is a very natural and common setup because very often when we're doing machine learning, there is lots of data that we need. So we would often outsource this data gathering task to others or just gather from many data sources. And so one example is crowdsourcing, where basically you can use platforms like Amazon Turk to ask users that they label data for you. If you can click, then a second example is when you're gathering data from different laboratories, because let's say biological data can be very expensive, so they can collaborate. If you can click, please. So the next example is of federated learning, where basically Google or other companies can ask private devices that they share some information based on gradients, and then they can learn one horizontally. And lastly, yes, you can click. If you would gather data from online websites by crawling, then you're essentially getting data from different websites. And so now what happens is that, of course, there are, again, issues with data corruption that you could expect. Basically, the sources are external and you cannot completely trust them. So it is plausible that some corruption would enter into your data. But if you can click, so basically, it is natural that we consider a situation where basically a subset of the sources gives you good data, and then a subset of the sources gives you potentially corrupted data. So essentially, we can work in a worst case setup when there is an adversary that can once again manipulate data. The crucial assumption that we're making is that some of our data sources, yes, might be accessible for corruption, but then others wouldn't. Maybe some of these data sources would be very good at providing clean, high quality data. And if you can click yes, so basically what we would ask now is how much we can learn in such situations. So can we hope that we can do learning well? If we have an adversary that is controlling some of the sources, but at least we have this extra information that like there is these groups of data and the subset of them are completely clean. If you can click, thank you. So then, okay, this is obviously quite a relevant setup. And so people have looked into some related problems. So we have already discussed the single source case when you have one data set and a subset of it is corrupted. So another paper that is relevant and then also line of work after that was on unsupervised learning with the same type of considerations. So basically you have different data sources and you're learning one density function, like this paper here is on discrete densities, but then also continuous densities later on as well. And so what we would look at now is the supervised learning version of this problem. There is also research on Byzantine robust optimization. Maybe you have seen that. So if you're training distributedly on some cluster, then very often what happens is that the nodes are not very stable and reliable. So people look at optimizing robustly in such setups, basically ensuring that gradient updates that are faulty wouldn't hurt you. So this is very optimization specific, and it also has this distributed anchor that we don't have here. Basically, we assume that our data is centralized, and we would look at the limits of any learning procedure, not just those based on SGD. And then lastly, there is the notion of collaborative learning, which is about like multiple parties collaborating with each other. And in such context, people have looked into robustness, but in such context also what is happening is that each of the agents learns their own model, whereas now we would look at a situation where we're only learning one model that should serve the good participants well. If you can click, thanks. So I will explain now what is our training data generation process. Basically, once again, what is the exact adversarial model that we look at? So basically, we start with this set of sources. Like now, instead of this kind of one batch of data, we have a set of data sets, basically these bins on the picture, and then the adversary can get access to a random subset of these bins. So previously we had that the adversary can access individual data points, whereas now it can access individual bins. And if it has this access to individual bins, then it can basically do anything that it likes within these bins. So in this red bin that is in the middle, it can manipulate all or some of these data points. And like once again, you can think of this blue dot set as input-output pairs. So the adversary can completely manipulate both inputs and outputs. And if you can click, there is some notation that I want to introduce. So we would denote the number of sources by capital N and the number of data points per source as small n. And for simplicity, we assume that this number is equal across the sources. And so then C is the set of corruptible sources, basically those that the adversary can access, and we assume that its size is equal to alpha hens. So it's a subset of our data sets that is of size less than half. So then the adversary takes in this clean data that we denote by S, and it outputs corrupted data sets by this only constraint that it cannot change those points that are not in C. So it cannot change the blue bins at all. If you can click, we can go to the formal definitions now of like what do we actually mean by learnings. So like notice that we now have this multi-source structures. So learner would be a function that would take a collection of data sets and would output a hypothesis. So crucially, this learner knows that there is this group structure that it can exploit. And so then we should define what is good learning. So as usual in learning theory, we will define this as a property of the hypothesis space. So we would say that the hypothesis space is alpha adversarially back-learnable if there exists a learner that can learn it well against any adversary. And like, what does this formally mean? So there would exist a learner that, if it has access to a sufficient amount of data per source, can with high probability output a hypothesis that is close to optimal, and it can do so against any adversary. So to formalize just this equation, basically so like recall that S is our clean data set, then A of S is the output of the adversary, which is just this corrupted set of data sets, and then L of A of S is the hypothesis that is learned by our learner based on the corrupted data set. And we care about how good is this on the test data. If you can click, please, thanks. So basically now we can show more optimistic results. So we can show that for most standard hypothesis spaces, they are also alpha adversarially back-learnable. And recall this uniform convergence property that is the key assumption that we need. So this just states that given access to some data, the empirical risk of a hypothesis is a good approximation of the true risk, and it's a good approximation kind of uniformly over the whole hypothesis space. So this is so this basically says that the supremum between the absolute difference of empirical and true risk is upper bounded by a function that will disappear with more and more data that we have access to. And so this is a classic property in learning theory. It's equivalent to clean data pack learnability when you have binary classification. Actually, this result that I present here also holds for an arbitrarily bounded loss function. And so what we have shown is that this classic property also implies that there exists a learner that can learn well in this multi-source data setup, even against the malicious adversary. So if you can click, then I can also show you some specific convergence rates. So this function that is controlling the uniform convergence property. This often would scale with 1 over square root of the number of data points. So in such cases, we can show a specific upper bound on the gap between what we're learning and what we and what is optimal. And this upper bound has two terms. If you can click, then we'll see the first one. So what is this term? So recall that 1 minus alpha is the fraction of the clean data sources, those that cannot be touched. So then 1 minus alpha times capital N is the number of clean sources we have, and then 1 minus alpha times pen times N is the number of clean data points that we have in these clean data sources. So if our learner would know these clean data sources, then clearly it will only work with them, and then this is what they would get as a bound on their loss. But then there is the second term. If you can click, so then this term is essentially what we pay, because we don't know what are these clean data sources, because the learner doesn't know what the adversary did. And so then this term would disappear when alpha is zeros. So in this in a fully clean data set, there is no problem, there is no term like that. But in case that there is data corruption, then you would pay this term that also only depends on the number of samples per source. So this means that if this algorithm would have to work, then we should grow the number of samples per source, and it is not enough that we only increase the number of sources. And in our paper, we showed that this is actually necessary. So we proved a lower bound, which depends on the size of the individual data sets, this small n alpha. And this meant that you cannot learn completely when you just increase your number of data sources. And the follow-up paper actually showed that this bound is tight. So basically this term that is in red is the optimal dependence on the local sample size. If you can click, please. So just very, very briefly, because we're running out of time, what is the learner that is actually achieving these things? Well, so it's actually very natural. So like you have this set of data sets, and you have to kind of decide which ones are corrupted, which ones are not, and essentially use those that you trust. And this is exactly what we will do. Basically, what we do is that we measure some pairwise distances between our data sets, and then we can create a set of trusted data sets, basically those that we consider to be clean based on these distances. So formally, we say that we will trust one data set if it is close in this distance measure to at least half of the other data sets. And then once we would collect this set of trusted data sets, then we can just learn PRM. We can learn by empirical risk minimization. By the way, notice that this is a statistical learner, so it's a function that is mapping data to a hypothesis. It's a completely different question whether it is computationally efficient, and unfortunately, in many cases it is not, but at least there exists a mapping between the data and the hypothesis. And then why would this work? Like basically, why is like when would the filtering work? So kind of one of the assumptions that we're making is that for the clean data sets, this distance measure would be small. So basically, clean data sets would be close to each other. And for a corrupted data set, we hope that either it's far away, and this means that we can kick it out with the filtering, or it's nearby, but then we have to prove that it will not hurt our optimization much. And so why would this happen? Well, it could happen because basically, if a corrupted data set would enter through the filtering, then this means that it's close to at least half of the other data sets. And in particular, this means that it's close to at least one of the clean data sets, because we assume that the clean data sets are more than half. And so this is roughly why we hope that this would work. And if you can click, I can show you what exactly distance measure we've used. So essentially what distance we would need needs to satisfy that for clean data sets, this distance is small. And on the other hand, if we have one clean data set and a corrupted data set, then if they are close, then it must be that the corrupted data set does limited damage. And there is one distance that we were aware of that actually did the job for us. So this is the so-called discrepancy distance. This is just this is very popular in the fields of domain adaptation and transfer learning. And essentially, what it does is that it looks for the maximum difference between the empirical risk of a hypothesis on these two data sets. Basically, there is these two kind of data sets that you compare, and you can look at how much does a hypothesis differ in terms of its performance on these two data sets, and you can take the supremum over the hypothesis space. So this is essentially one notion of how much does your hypothesis space differentiate between different data sets. And like this is also actually one type of integral probability metric. If you can click, then this is my last slide, where I actually would just summarize and also kind of mention some other things that we did. So we showed, if you can click, that essentially in the setup, you can actually learn even against the malicious adversary. So within this model of data sources that can be maliciously corrupted, you can actually achieve pack learnability. If you can click, then we've also looked at some more practical methods for learning from such data sets. So the first one, if you can click, is a paper where we showed, yes, basically both we can have. So, so for the first one, this is a paper where we have looked at ways that we can weight our data sets by comparing them to some small reference clean data set. And in the second paper, which was recently accepted at the TMLR, what we did was that we had also guarantees for fairness. And in addition, this algorithm there achieves good practical performance. So thank you very much for the attention. And I'm happy to receive any questions from you. Thanks.
Yeah, thanks a lot for the good talk. Clearly you did a very great work on learning theory on adverse serial corruptions on learning algorithm. In the textbook, I only learned the pack learning. Now I have adverse serial pack learning. It is very exciting theoretical tools to handle many aspects. Therefore, I'm thinking whether I can use your pack learning theory to handle more aspects. For example, maybe explainability, adversarial robustness, or something, or some other learning algorithm like unsupervised learning or semi-supervised learning. What do you think?
That's a wonderful question. So I have seen works that provide theoretical kind of pack learning guarantees for explainability, for privacy and for others, and especially for adversarial robustness. And so basically what you typically need is to have one well-defined notion of your loss when you consider this extra constraint. So in the case of the fairness, we had this gamma, which was a kind of well-defined quantity that we can optimize. And for the case of adversarial robustness, this is basically your kind of worst case risk, like so like you would look at the whole region around your data point, and you would look at what is the probability that is misclassified. But in any case, yes, once you have this type of notions, then you can try to study how much you can learn them from a theoretical perspective. And of course, also like you can incorporate these notions of training time adversaries. This is just one model that can handle like whole possible issues with a subset of your data, making your algorithms hopefully more robust.
I see. That's great.
Thank you. That's
you.
a great question. Mm-hmm.
Yeah, thank you very much for your great talk, and thank you for your good questions.
Thank you also, and thank you also that you handled this problem with the screen sharing. That was very nice. Thanks.
Yeah, we are happy to have you. If you have time in the near future, welcome us.
Mm-hmm.
We are in.
Oh, thank you very much. Yes, yes.
Yeah.
Sorry.
We will have time in the future. Welcome us.
Yes, definitely.
Visit us. Sorry. Yeah. We are in the Nihonbashi office in the center of Tokyo. It's really nice place near the center.
Thank you very much. Yes, thank you very much. Thanks a lot.
Yeah. Thanks. All right. This is the end of today's seminar. Thanks very much. Bye-bye.
Thank you. Bye.